You've heard about quantum computing, maybe quantum cryptography, but there's one quantum technology already working in your pocket, your hospital, your GPS satellite right now: quantum sensors. Not lab experiments, not 5 years away. They're measuring magnetic fields 10 billion times weaker than a fridge magnet, timing signals to 1/1000th of a second, detecting gravitational shifts invisible to classical tech. They find oil fields 2 miles underground. They map brain activity without cracking your skull. They navigate submarines when GPS goes dark. The global market hit $377 million in 2024, and it's projected to explode past $1.2 billion by 2032. Atomic clocks grabbed 32% of that revenue because telecom carriers and data centers need nanosecond perfect synchronization. Nitrogen vacancy diamond sensors grow at 17% annually because they work at room temperature while competitors freeze. Cold atom interferometers lead with 45% market share after decades refining laser cooling. Every type leverages quantum mechanics differently: superposition, entanglement, tunneling, to measure what classical sensors miss. Which sensor detects what? How do atoms measure gravity? Why does a diamond effect read magnetic fields? What happens when you cool rubidium to near absolute zero? If you value documented physics and real engineering like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual, using sources from Nature Communications, published August 2024 on cold atom interferometry aboard the International Space Station, and from the Mordor Intelligence Market Report, dated July 8, 2025, tracking atomic clock dominance in quantum sensor deployments, sources that drill into hardware specifications and field trial data rather than marketing fluff. Now back to the information. Nitrogen vacancy centers sit inside diamond crystal lattice. A nitrogen atom replaces one carbon. The adjacent spot stays empty. That's the vacancy. Two charged states exist, neutral NV0 and negative NV-. NV- gets the work. A nitrogen atom brings 5 valence electrons. 3 bond to neighboring carbon. 2 remain as a lone pair. The vacancy holds 3 valence electrons. 2 form a quasi-covalent bond. 1 stays unpaired. Overall symmetry stays trigonal under the C3V group. In NV-, an extra electron joins the vacancy, forming a spin 1 pair. Ground state becomes triplet 3A. Excited state becomes triplet 3E. A metastable singlet sits between them. These defects occur naturally, but yield better control when made artificially. Ion implantation with electrons, protons, neutrons, ions, gamma photons creates them. Irradiation followed by annealing above 700 degrees Celsius converts substitutional nitrogen into NV centers. The creation process matters. Natural diamonds contain nitrogen already. Type IB diamonds have nitrogen concentrations exceeding 100 parts per million. But those nitrogen atoms sit as single substitutions. You need the vacancy next door. Electron beam irradiation at energies around 2 megaelectron-volts knocks carbon atoms out of lattice positions, creating vacancies throughout the crystal. Then heat it. 700 to 1000 degrees Celsius for hours. Vacancies diffuse through the lattice. When a vacancy meets a nitrogen atom, they bond. The NV center forms. Concentration control comes from initial nitrogen doping during chemical vapor deposition growth. Labs grow synthetic diamond on silicon substrates. Microwave plasma decomposes methane. Carbon atoms deposit layer by layer. Add nitrogen gas to the mix. Nitrogen incorporates. Concentration tunable from parts per billion to parts per million. After growth comes irradiation and annealing. Final NV density reaches 10 to the 11th per cubic centimeter in optimized samples. That's 100 billion per cubic centimeter, spacing around 100 nanometers. Perfect for ensemble measurements. Single NV centers require lower density. Implant nitrogen ions with nanometer precision. Control the dose. 10 to the 12 ions per square centimeter gives roughly 1 NV center per square micron after annealing. Quantum-limited single-spin measurements. Demand isolation. Energy levels shift with magnetic fields, electric fields. Temperature, strain, that makes them sensors. Atomic size gives nanoscale resolution. Spin coherence lasts milliseconds even at 300 Kelvin. Green light excites the center. Red photoluminescence comes back. The emission intensity depends on the electron spin state. That's optically detected magnetic resonance. You initialize the spin optically. You read it out optically. No cryogenics, no vacuum. The NV center operates at room temperature, sitting on a benchtop or inside a living cell. Researchers at Fraunhofer Institute and RMIT University demonstrated in July 2022 that laser threshold magnetometry using NV diamond delivers 10 times better precision than state-of-the-art for brain magnetic field mapping. Their laser cavity held an NV-doped low-absorbing diamond as the gain medium. Magnetic field sensitivity hits sub-picotesla range. That's 10 to the negative 12 Tesla. For context, MRI magnets run 1 to several Tesla. Earth's field sits around 50 microtesla. Brain signals from neurons range 10 to 100 femtotesla. Magnetoencephalography needs sensors with noise below 5 femtotesla per root hertz and low-frequency knee under a few hertz. Squid magnetometers dominated this space for decades, but NV sensors now compete without liquid helium. Medical imaging uses them, neurology uses them, mineral prospecting, electronic warfare, nanoscale materials. Research, you embed NV diamonds in atomic force microscope tips using focused ion beam milling. The cantilever maps stray magnetic fields and studies nanomechanical properties with spatial resolution below 10 nanometers. Optical excitation at 532 nanometers initializes the spin. Microwave pulses manipulate it. Photoluminescence between 600 and 800 nanometers provides readout. Nitrogen vacancy centers detect single electron magnetic resonance, enabling chemical structure identification at the single molecule level. They measure temperature via zero field splitting temperature dependence. Pressure sensitivity comes from strain-induced energy level shifts. Electric field sensing uses stark shifts, multiple physical quantities from one sensor. Biocompatibility allows insertion into living cells. Researchers measured lithium ion concentration in metal organic frameworks at room temperature using NV relaxometry. They tracked magnetic nanoparticles for drug delivery. They imaged current distribution in integrated circuits. Diamond is chemically inert, mechanically robust. Optically transparent from UV to infrared. Surface chemistry matters. Oxygen termination stabilizes NV minus charge state. Hydrogen termination destabilizes it. Near-surface NV centers within 10 nanometers suffer degraded performance from surface charges and adsorbate. Researchers develop surface treatments, oxygen plasma, chemical vapor deposition of thin diamond layers, molecular functionalization, to protect shallow NV centers while allowing target molecule attachment. Coherence time determines sensitivity. Bulk diamond NV centers show spin coherence exceeding 1 millisecond. Near surfaces, it drops to microseconds. Magnetic field sensitivity scales as 1 over square root of coherence times square root of detected photon rate. For DC magnetometry, sensitivity reaches sub-nanotesla per root hertz. AC magnetometry, bandwidth extends to gigahertz. Commercial systems exist. Companies ship NV magnetometers for non-destructive testing, geological surveys, biomedical research. Market value for NV diamond sensors in 2024 reached tens of millions, and it's climbing 17% per year according to multiple independent market reports from Fortune Business, Insights, and Mordor Intelligence. 17.21% CAGR through 2030. Specifically, because room temperature operation removes the infrastructure barrier that kills squid adoption in field applications. Cold atom interferometry splits atomic matter waves to measure inertial forces and gravity with quantum precision. You start with rubidium-87 or cesium-133 atoms. Trap them in a magneto-optical trap. Laser beams from 6 directions plus a magnetic field gradient slow and cool the atoms to microkelvin range, below 1 millikelvin. Below 1 microkelvin with subdoppler cooling techniques, rubidium vapor at room temperature moves at hundreds of meters per second. Cooled atoms creep at centimeters per second. Quantum mechanical wave nature emerges. De Broglie wavelength becomes picometers. Coherence extends. Now apply a sequence of laser pulses. First pulse creates superposition. Atom simultaneously moves and doesn't move. Beam splitter for matter. Second pulse, after time, T lets paths accumulate phase difference from acceleration or gravity. Third pulse recombines the paths. Interference pattern emerges. Population in ground versus excited state depends on the phase accumulated. That phase encodes acceleration. Gravimeters measure local gravitational field. Accelerometers measure acceleration. Gyroscopes measure rotation. Gravity gradiometers measure spatial derivatives of gravity. The basic measurement principle emerged in the 1990s. Stanford demonstrated atom interferometer gravimeter in 1992. Sensitivity reached parts per billion. By 2006, the same group showed a cold atom gyroscope meeting the stability requirements for high accuracy navigation, 10 to the negative third degrees per hour over 84 minutes. France's SOIRTE lab built a transportable cold atom gravimeter that measured gravity variations below 10 to the negative ninth G, that's 1 nanometer per second squared, reported in Science Reports, Volume 8 in 2018. Absolute measurement traceable to atomic constants. No calibration drift. Classical corner cube gravimeters require regular recalibration against reference sites. Atom interferometers self-calibrate. The gravity measurement links directly to photon momentum, atomic mass, pulse separation time. LNE CERTI gravimeter participated in international absolute gravimeter comparisons since 2009. 6 Chinese cold atom gravimeters joined the 10th international comparison in 2017. Results matched classical gravimeters within measurement uncertainty. Portable systems weigh tens of kilograms, fit in a van, operate in the field. Marine gravimetry works. A French team reported absolute marine gravimetry with matter wave interferometry in Nature Communications, Volume 9 in 2018. Ship-mounted system measured gravity over ocean. Sensitivity hit tens of microgal per root hertz. Tidal gravity measurements in the lab reveal ocean loading effects and record-distant earthquakes. A Berkeley Hills survey in Science Advances demonstrated mobile atomic gravimeter surveying terrain with uncertainty around 40 microgal. They determined subsurface rock density from vertical gravity gradient, oil prospecting, mineral exploration, underground cavity detection, civil engineering foundation surveys, earthquake prediction networks, volcano monitoring. Climate science needs gravity missions, tracking ice sheet mass changes and groundwater depletion. The vertical gravity gradient technique deserves attention. Measure gravity at 2 heights simultaneously. The difference divided by height separation gives gradient. Units are Eötvös. 1 Eötvös equals 10 to the negative 9th per second squared. Typical Earth gradient around 3,000 Eötvös. Underground cavities show negative anomalies. Dense ore bodies show positive anomalies. Atom interferometer. Gravity, gradiometers measure both accelerations in the same instrument. 2 atom clouds at different heights. Same laser pulses interrogate both. Differential measurement cancels common mode vibrations. McGurk and collaborators demonstrated sensitive gravity gradiometry in Physical Review, a Volume 65 in 2002. They measured gradient with sensitivity 3 times 10 to the negative 9th per second in 1 second measurement time. That resolves density variations of a few percent over meter scales. Applications in tunnel detection, archaeological surveys, unexploded ordnance location, aquifer mapping, military interest obvious, commercial interest growing. Europe's Carioca project kicked off Phase A in January 2024. Cold atom rubidium interferometer in orbit for quantum accelerometry. Goal is improve Earth gravity measurements from space while advancing climate science. Water mass distribution changes alter Earth's gravity field. Detection would enable monitoring ice sheets, groundwater, floods, droughts. The predecessor missions, Grace and Grace. The FO used microwave ranging between 2 satellites. Measure distance changes as satellites orbit. Distance variations. Map gravity field. Resolution around 300 kilometers. Mass change. Sensitivity 5 centimeters water height. Equivalent. Carioca. Targets improvement by factor 5 to 10. Resolution 150 kilometers. Mass change 0.5 centimeters per year for long-term trends. That requires atom interferometry. Longer interrogation times in microgravity. Better acceleration sensitivity. Single satellite design possible instead of formation flying. Laser links, ground stations for absolute position reference. Technology development ongoing. European Space Agency and CNES coordinate. Atom interferometer. Payload contracts awarded. Launch window around 2030. Spaceborne quantum sensors register 18.21% CAGR, according to Mordor Intelligence, as climate missions and fundamental physics experiments validate low orbit operation. NASA's Cold Atom Lab operated aboard the International Space Station since 2018, studying ultra-cold atoms in microgravity. Pathfinding experiments with ultra-cold rubidium-87 reported in Nature Communications, August 2024. 3-pulse Mach Zander interferometer studied ISS vibrations. Ramsey shear wave interferometry created interference patterns observable over 150 milliseconds free expansion time. Photon recoil measurement demonstrated remote calibration to fundamental constants. Extended freefall in microgravity enables longer interrogation times. Interrogation time t directly multiplies sensitivity. Ground systems limited to t equals 1 second by freefall height. Need a 10-meter tower. Space removes that limit. T of 10 seconds improves sensitivity by 10 times. 100 seconds by 100 times. Fundamental physics tests become possible. Equivalence principle tests. Gravitational wave detection. Dark matter searches. Large momentum transfer techniques boost sensitivity further. Standard atom interferometry uses 2 photon transitions, imparting 2 photon momenta. Large momentum transfer uses block oscillations or multi-photon transitions, imparting tens or hundreds of photon momenta. Phase shift scales with momentum transfer. More momentum means more signal. Demonstrated with up to 24 photon momentum transfer in Physical Review, Letters, Volume 100, in 2008. Composite pulse techniques improve robustness, adiabatic rapid passage, optimal control pulses. Techniques reduce systematic errors from laser intensity fluctuations and detuning. Miniaturization progresses. Photonic integrated circuits replace bulk optics. Grading magneto-optical traps on chips. Pyramidal hollow mirrors for compact traps. Subdoppler cooling in chip-scale systems achieves 15 microkelvin. Repetition rate reaches 20 Hz. Interrogation time 0 to 4.5 milliseconds gives sensitivity delta G over G of 2 times 10 to the negative sixth. Cold atom quantum sensor companies include AOSense, Muquans, M squared lasers, SB Quantum, Atomionics, Robert Bosch invests, Microchip Technology supplies lasers, research consortia pool intellectual property, and share fabrication facilities to scale. Government funding for atom interferometry and navigation and defense drives development. United States allocates funding for GPS-denied navigation. Submarines, underground facilities, urban canyons, quantum accelerometers and gyroscopes enable inertial navigation without external signals. Drift rates far below mechanical systems. UK invests £40 million in quantum navigation programs. China establishes over 50 research collaborations between universities and foreign institutions focused on quantum sensors in 2025. India grows at 18.8% CAGR through 2035, with government-funded projects contributing 40% of research outputs in 2024. 15 quantum sensing startups launched in China in 2024, focusing on industrial applications. Rydberg atoms detect electric fields with exquisite sensitivity and unprecedented bandwidth. A Rydberg atom has one electron excited to a very high principal quantum number En, 50, 60, 100. Electron orbit balloons. Transition dipole moments scale as n squared. Polarizability scales as n7. Tiny electric fields cause massive energy shifts. Energy spacing between adjacent Rydberg states scales as 2 over n cubed. Small gaps. Microwave and radio frequencies couple directly to Rydberg transitions. Coverage spans DC to terahertz. Alkali atoms work well. Rubidium 87, cesium 133, room temperature vapor cell, centimeter size. Probe laser excites ground state to intermediate level. Coupling laser excites intermediate to Rydberg state. Electromagnetically induced transparency opens a narrow transmission window. External electric field causes Auler-Towns splitting of the transmission peak. Split magnitude measures field strength. All optical readout, SI traceable measurement. Rydberg electric field coupling determined by atomic wave functions, calculable from first principles, measurable with ultra-high precision spectroscopy. NIST develops fiber-coupled Rydberg sensors. National Institute of Standards and Technology Communications. Technology Lab builds Rydberg atom-based RF field probes. Sensitivity demonstrated below 1 microvolt per centimeter per root hertz. Bandwidth, DC to terahertz. Confirmed, instantaneous bandwidth 100 megahertz. Frequency tuning by changing Rydberg state selection. Same sensor covers AM radio, FM radio, Wi-Fi, Bluetooth, cellular, radar bands without hardware changes. Absolute calibration without reference standards. Probe and reference antennas both introduce errors and uncertainties. Rydberg atom provides fundamental calibration. Electric field strength directly traceable to Planck constant. Electron charge, atomic mass. NIST published Applied Physics Letters, Volume 102 in 2013, showing single photon detection efficiency 50% at 1,310 nanometers within GAAS NP SPAD gated at 1.25 gigahertz. Later work pushed sub-1 Hz resolution at radio frequencies using Rydberg mixer. Applied Physics Letters, Volume 113 in 2018, demonstrated RF power measurement traceable to redefined SI using radiation pressure. Communications, reception works. Rydberg atoms act as electrically small antennas, detect amplitude modulation, frequency modulation, phase modulation, superheterodyne reception with atom-based local oscillator. Quantum receiver published results, detecting guitar recording using Rydberg EIT. Music signal modulated onto RF carrier. Carrier frequency matched Rydberg transition, demodulation via transmission spectroscopy. Audio reconstructed. Military interest focuses on direction finding and spectrum analysis. Rydberg sensors measure vector electric field. 3 orthogonal measurements give field direction. Imaging applications demonstrated. Array of Rydberg sensors forms en RF camera. Spatial resolution below wavelength. Waveguide field mapping without perturbing field. Insert vapor cell, not metal probe. Quantum radar concepts explored. Companies commercialize. Rydberg Technologies in Ann Arbor spun out from University of Michigan. Products include an RF field measurement system spanning low frequency to millimeter wave, metrology, antenna testing, electromagnetic compatibility. Collaborates with defense and government agencies. Scientific publications from Shaanxi University, China, University of Science and Technology of China, South China, Normal University, National University of Singapore, document sensitivity improvements, bandwidth extensions, modulation detection schemes, Science Bulletin, Volume 69, published March 2024, reviewing Rydberg atom electric field, sensing for metrology, communication, and hybrid quantum systems. Authors covered EIT, EIA, amplitude modulation, frequency modulation, optical homodyne, readout, microwave superheterodyne, or multi-wave mixing. Target applications included quantum networking, quantum computing interfaces, secure communications, superconducting quantum interference devices measure magnetic flux with femtotesla sensitivity. SQUID consists of superconducting loop interrupted by 1 or 2 Josephson junctions. DC SQUID has 2 junctions. RF SQUID has 1. Josephson junctions are thin insulator barriers between superconductors, allowing Cooper pair tunneling. Quantum interference between paths around the loop makes voltage across device, periodic, and external magnetic flux. Period equals 1 flux quantum, 2.068 times 10 to the negative 15 Tesla meters squared. That's h over 2e. Planck constant divided by twice electron charge. Macroscopic quantum effect. Voltage modulates with field. Readout electronics locked to flux quantum periodicity. Sensitivity reaches 3 femtotesla per root hertz in optimized low temperature systems. That's 3 times 10 to the negative 15 Tesla per root hertz. 5 times 10 to the negative 18 Tesla, detectable, with averaged measurements over days. For comparison, refrigerator magnet produces 10 millitesla, earth field 50 microtesla. Biological signals 10 to the negative 9 to 10 to the negative 6 Tesla. Operation requires cryogenic cooling. Low temperature squids use niobium. Critical temperature 9 Kelvin. Liquid helium bath at 4.2 Kelvin. High temperature squids use yttrium, barium, copper oxide. Critical temperature 90 Kelvin. Liquid nitrogen cooling at 77 Kelvin. Cheaper, easier handling, lower sensitivity. Still good for many applications. Squid magnetoencephalography. Measures brain magnetic fields. Helmet array with hundreds of squids, maps neural currents. Magnetocardiography records, heart electrical activity. Magnetic field noise below 5 femtotesla per root hertz, with frequency Ni below a few hertz required. Squid meets specifications. Magnetic property measurement system sold by Quantum Design. MPMS-3 represents 40 years of development. Superconducting magnet provides fields up to 7 Tesla. Temperature control 1.8 to 400 Kelvin with oven option extending to 1000 Kelvin. Moment sensitivity 10 to the negative 8 EMU for fields below 2500 Oersted. Sample moves through pickup coils. Coils connect to squid isolated from applied field. Voltage versus position gives magnetic moment. Applications include superconductor characterization, magnetic material studies, nanoparticle analysis, geophysical exploration uses squids, oil prospecting, mineral surveys, earthquake prediction, geothermal energy, surveying, 3-axis magnetometer systems measure earth field variations, Schumann resonance detection, very low frequency electromagnetic waves. Gravitational wave detectors employ squids reading out motion of test masses. Gravity probe. B used 4 squid-based gyroscopes testing general relativity. Scanning, squid microscopy. Images, magnetic fields with micron resolution. Immerse squid in liquid helium, scan over surface, map flux from currents, magnetic domains, vortices and superconductors. The biomagnetism applications demand specific performance. Human heart generates magnetic field around 50 picot-sla at chest surface. Brain signals weaker, 50 to 500 femtotesla depending on source depth and orientation. Background noise in unshielded environment reaches nanoteslas or microtesla from power lines, vehicles, elevators, trains. Magnetically shielded rooms use layers of mu metal, reducing external fields by factors exceeding 1000. Residual field inside room drops to tens of nanotesla. Squid magnetometers operate inside these rooms. Magnetoencephalography systems position array of squids around head. Helmet design, 64 to 306 channels typical. Measure magnetic field pattern from brain activity. Inverse problem reconstructs current sources in brain. Millisecond temporal resolution. Centimeter spatial resolution. Applications include epilepsy seizure localization, pre-surgical brain mapping, cognitive neuroscience research, traumatic brain injury assessment, magnetocardiography, maps heart electrical activity without electrodes, T-wave analysis, QRS complex morphology, fetal magnetocardiography through mother's abdomen, commercial MEG systems sold by Electa, CTF Systems, Yokogawa, Ricoh, capital cost $1 to $3 million. Operating cost dominated by liquid helium consumption, tens of thousands per year. That's where atomic magnetometers promise disruption. NASA employs squids for remote non-contact sensing, Earth magnetic field monitoring from space, brain activity measurement in pilots, star cryoelectronics. Commercialized squid sensors and PC-based control electronics funded through NASA SBIR contracts, biomedical imaging, non-destructive testing, geophysical exploration, basic research. Sensors detect magnetic signals from neural activity in brain. Magnetocardiography identifies sudden cardiac death risk, 300,000 deaths per year in the United States. Ultrasensitive detection enables low-field MRI. Precession fields in microtesla range instead of Tesla range. Aircraft wheel rim crack detection. Jet engine turbine blade inspection. Quantum computing readout. D-wave quantum annular uses squids constructed from niobium loops as qubit readout. Each squid reads one flux qubit. 2048 qubits in D-wave 2000Q system. 2048 squids. Cryogenic multiplexing distributes signals. Readout speed determines annealing time. Faster. Squid electronics enable faster optimization cycles. Atomic magnetometers compete without cryogenics. Spin exchange relaxation-free magnetometers achieve sensitivities approaching squid levels. 7 to 10 femtotesla per root hertz demonstrated. Alkali vapor cell, rubidium or potassium. Near zero magnetic field environment. Pump laser polarizes atomic spins. Probe laser measures precession. Larger sensing volume than squid, cubic centimeter versus millimeter squared. No cryogenic infrastructure. Room temperature operation. Portable. Medical applications explored for decades. Magnetoencephalography systems under development. Challenges include operating in magnetically shielded rooms and field gradients. Optomechanical sensors combine optical cavities with mechanical resonators for acceleration and force measurement. Membrane or cantilever forms one mirror of Fabry-Perot cavity. Mechanical resonator responds to forces. Displacement changes cavity length, resonance frequency shifts, readout via optical transmission or reflection. Shot noise limited displacement sensitivity. Radiation pressure couples back, cooling and squeezing possible. Room temperature operation demonstrated, but cryogenic systems reach quantum limits. Silicon nitride membranes achieve quality factors exceeding 1 million at 4 Kelvin, 300,000 at 300 Kelvin. High stress reduces dissipation. Tensioned membranes, phononic crystals, soft clamping designs, mechanical frequency tens of kilohertz, optical finesse thousands, optomechanical coupling strength scales with cavity finesse and mechanical frequency. University of Arizona and University of Michigan demonstrated entanglement-enhanced optomechanical sensing in Nature Photonics in 2023. 2 membrane sensors, squeeze light distributed to both quantum entanglement between optical fields. Measurement sensitivity improved 40%. Speed increased 60% compared to classical. Acceleration sensitivity, 10 nanoG per root hertz over 30 hertz bandwidth. That's 10 times 10 to the negative 9 times acceleration of gravity. Precision better than traditional inertial sensors. GPS-denied navigation, autonomous vehicles, dark matter detection, membrane-based optomechanical accelerometers proposed as ultralight dark matter detectors. Vector coupling to dark matter field via material inhomogeneity. Silicon-3 nitrogen-4 membrane cavity mounted to 4 Kelvin copper plate, photothermal tuning scans, 39 kHz mechanical resonance, shot noise limited readout, radiation pressure, feedback cooling, cryogenic operation, Bayesian matched filter search conducted. No signal observed but validates scalable approach. Optimized test masses and multiplexed arrays offer path to competitive constraints. Chip scale systems demonstrated, photonic crystal cavities integrated with nanogram test masses, acceleration resolution, 10 micro per root hertz for sub-milliwatt optical power. Bandwidth exceeding 20 kilohertz, dynamic range 50 decibels, picogram masses, radiation pressure, back action significant, strong optomechanical coupling enables quantum phenomena. Ponderomotive squeezing, ground state cooling, the engineering challenges multiply at scale. Thermal drift changes cavity resonance. Temperature control to millikelvin required. Vibration isolation critical. Seismic noise dominates below 10 Hz. Active feedback or passive springs needed. Acoustic noise couples through air and structures. Vacuum operation standard. Pressure below 10 to the -6 torr. Laser frequency noise couples to measurement. Pound-Drever Hall locking. Stabilizes laser to cavity. Residual frequency noise appears as displacement noise. Shot noise sets. Quantum limit. Higher optical power reduces shot noise but increases radiation pressure noise. Optimal power exists. Shot noise equals back action noise at standard quantum limit. Squeezing beats, standard quantum limit. Inject squeezed vacuum into unused cavity port. Reduces shot noise below vacuum noise. Radiation pressure correlates with reduced shot noise. Proper squeezing angle and homodyne detection angle. Extract correlated signal. Demonstrated below standard quantum limit in multiple experiments. Mechanical Q factor determines thermal noise. Higher Q gives lower thermal noise floor. Silicon nitride. Nanomembranes reach Q exceeding 10 million at millikelvin temperatures. Dissipation dilution in high-stress membranes reduces loss. Phononic crystal designs isolate mechanical mode from environment. Soft clamping with optimized support geometry. Material choices matter. Silicon nitride for membranes. Fused silica for cantilevers. Crystalline coatings for mirrors. Each platform has strengths. Companies develop products. Commercial interest in precision navigation, geophysical monitoring, inertial sensing for aerospace, NSF-funded projects for quantum-enhanced optomechanical accelerometers. COMA project achieved chip-scale optomechanical accelerometer with sub-micro-G resolution. Radiation pressure cooling to effective temperature, 1 millikelvin reduced thermal noise to 50 nanoGA. Squeezed light array with 2-element membrane accelerometer demonstrated. Torsion resonators based on silicon nitride, nanoribbons engineered. Chip-scale torsion pendula sensitive to gravity at micro-G level using frequency readout. Differential measurements cancel common mode acceleration. Test mass geometry determines coupling. Asymmetric mass distribution couples to gravity gradient. Pair of masses at different positions measure gradient directly. Quadrupole test mass couples to second derivative. Applications in gravity. Gradiometry for navigation and resource prospecting emerge as sensitivity improves. Single photon detectors enable quantum communications and low-light sensing. Superconducting nanowire single photon detectors use thin film meandering nanowire on active area. Photon breaks, Cooper pairs, resistance spike detected. Efficiency exceeding 95% at telecom wavelengths. Timing jitter, tens of picoseconds. Dark count rate below 1 per second. Cryogenic operation, liquid helium or closed cycle coolers below 4 Kelvin. Avalanche photodiodes operated in Geiger mode detect single photons at room temperature. Single photon avalanche diode, SPAD, reverse bias above breakdown voltage, absorbed photon triggers, avalanche, current rises in sub-nanosecond time to milliampere level, picosecond timing jitter. Pulse marks, photon arrival. Quenching circuit lowers bias to stop avalanche, dead time before next detection. Active quenching and passive quenching circuits. Silicon SPADs work ultraviolet to near infrared. Quantum efficiency peaks 50 to 70% around 550 nanometers. Dark count rate varies, hundreds to thousands per second depending on device and temperature. Cooling reduces dark counts. Gating improves performance. Bias raised only during expected photon arrival window. Reduces dark counts and after pulsing. RF interferometry cancels systematic background. NIST demonstrated in-GAA's in-P SPAD at 1,310 nanometers with 50% efficiency, gated at 1.25 gigahertz. Applications include quantum key distribution, time of flight ranging, LIDAR, fluorescence, lifetime microscopy, positron emission tomography, quantum optics experiments, single molecule imaging, free space optical communications, satellite quantum communication, commercial products from PicoQuant, ID Quantique, laser components, Excelidus, arrays of SPADs and CMOS for imaging, time-correlated single photon counting, 3D imaging, autonomous vehicle, LiDAR, smartphone depth sensors. Quantum key distribution demands specific performance. BB84 protocol requires single photon sources and detectors. Sender Alice generates random bit sequence, encodes bits into photon polarization or phase states, transmits over optical fiber or free space. Receiver, Bob measures with random basis choice. Alice and Bob compare bases publicly. Keep measurements where base is matched. That's the sifted key. Quantum mechanics guarantees eavesdropper. Eve disturbs quantum states. Error rate reveals Eve's presence. Privacy amplification and error correction generate final secure key. Detection efficiency directly affects key rate. Dark counts add errors. Timing jitter limits. Clock rate. In-GAAS, in-P SPADs dominate telecom wavelength quantum key distribution. Detection efficiency 50% at 1550 nanometers. Dark count rate 1000 per second typical. Gated operation at gigahertz reduces effective dark counts. After pulsing from trapped carriers causes correlated errors. Pulsed illumination helps. Commercial QKD systems from ID Quantique, Toshiba, Quantum C-Tech operate metropolitan distances up to 100 kilometers. Satellite QKD demonstrated. China's Michis satellite established quantum links ground stations thousands of kilometers apart. Single photon detectors in orbit, published in Nature, volume 549 in 2017. Entanglement distribution over 1,200 kilometers. Quantum teleportation over 1,400 kilometers. Single photon uplink and downlink channels tested. Fusion of multiple detector types creates advanced systems. Silicon photomultipliers combine arrays of SPADs with common readout. Large active area, photon number resolution. Single photon timing. Challenges include afterpulsing, trapped carriers releasing after dead time causing false counts. Timing jitter variations, temperature sensitivity. Trade-offs between efficiency, dark counts, timing resolution, dead time, maximum count rate. GHZ count rates demonstrated with optimized gating and electronics. Real implementations demand temperature stabilization. Thermoelectric cooling to 0 degrees Celsius or negative 20 degrees Celsius reduces dark counts by orders of magnitude. Passive quenching uses resistor. Simple. Slow recovery. Active quenching uses sensing circuit and transistor switch. Fast recovery, complex, adjustable dead time, discriminator, threshold matters. Too low catches noise, too high misses small avalanches. Optimization varies by application. Photonic integration advances. Waveguide, coupled SPADs, on-chip timing circuits, 3D stacked architectures, top die for SPAD array, bottom die for readout and processing, fill factor optimization, in-GAAS in P detectors for telecom wavelengths, silicon detectors for visible, germanium on silicon for extended infrared, avalanche region engineering, electric field profiling, guard rings reduce edge effects, single photon cameras, megapixel arrays, real-time photon tagging, time stamping at picosecond precision, data rates, terabits per second from large arrays, compressed sensing algorithms, event-driven readout, applications multiply, astronomy, photon-starved observations, medical imaging, ultra-low dose, industrial inspection, high-speed sorting, autonomous systems, perception and degraded visibility, quantum networks, entanglement distribution. PIR sensors measure photosynthetically active radiation using quantum principles. Miscellaneous quantum sensors include quantum voltage standards based on Josephson junctions, quantum current standards, quantum resistance standards using quantum Hall effect, quantum temperature sensors, fiber optic quantum sensors for distributed measurements, nanodiamond quantum thermometry, rare earth-doped crystal sensors, trapped ion sensors, neutral atom array sensors, color center sensors and silicon carbide, quantum dots, quantum well structures, two-dimensional materials like graphene for sensing, topological insulator sensors, hybrid systems combining multiple quantum platforms. Each type exploits specific quantum phenomena. Market forces drive adoption. Global quantum sensors market valued $377.3 million in 2024, projected to reach $1,211.5 million by 2032. CAGR 15.8%. North America dominates with 33.5% market share in 2024. Continuous technological advancement in quantum computing spills over to sensor development, demand for accurate early diagnostic tools in healthcare, precision measurements in advanced manufacturing, robotics, automation, telecom infrastructure requirements, space-based applications, defense and security, atomic clocks lead market, quantum gravimeters and gradiometers fastest growing at 16.44%. CAGR, as Earth observation satellites and oil gas exploration demand higher resolution mass density maps. Quantum magnetometers, service neurology, mineral prospecting, electronic warfare. Quantum accelerometers and gyroscopes support inertial navigation in GPS-denied environments. Technology diversification broadens markets but strains supply chains. Diamond growth chambers, cesium rubidium vapor cells, high coherence laser diodes require specialized manufacturing. Ecosystem players form consortia pooling IP and co-investing in shared facilities. Economies of scale anticipated to satisfy multi-sector demand. Spaceborne applications surge 18.21% CAGR as climate monitoring, fundamental physics, positioning, navigation, timing satellite missions validate low-orbit operation. European Space Agency roadmap targets gravitational wave detection and optical clock time transfer, catalyzing component miniaturization and radiation-tolerant packaging. Integration with AI and machine learning enhances data analysis, enabling accurate predictions and real-time decision-making in applications. Generative AI simulates and optimizes quantum sensor designs, leading to more efficient and sensitive devices. China quantum sensor sales expand at 20.3%, a CAGR from 2025 to 2035, fueled by advancements in precision measurement and government-backed research, investments in navigation, defense, scientific applications. Domestic players develop quantum accelerometers and magnetometers, meeting industrial and military requirements. Strategic collaborations with global research institutions enhance innovation and production. High-tech manufacturing zones integrate quantum sensing into industrial automation and satellite systems. Over 15 quantum sensing startups established in 2024, focusing on industrial applications. Government-funded projects contributed 40% of research outputs in 2024. India quantum sensors. Industry grows 18.8% between 2025 and 2035, driven by national initiatives in space, defense, navigation. Private and public laboratories invest in high-precision atomic clocks and magnetometers. Collaborations with universities and global technology partners facilitate technology transfer and prototype development. Industries, including autonomous transport to geophysics. Telecommunications progressively integrate quantum sensors to enhance operational accuracy. 50 research collaborations launched between domestic universities and foreign institutions in 2025. Quantum sensor prototypes in defense applications increased 30% in 2024. United Kingdom quantum sensor adoption expands 14.3% CAGR from 2025 to 2035, driven by defense modernization and smart infrastructure projects. Universities and research centers develop atomic gravimeters and ultra-sensitive magnetometers. Collaborative efforts with European and North American technology firms boost product innovation. Government support for metrology and space-based navigation applications strengthen demand. Commercial sectors, including oil exploration, construction, transport, integrate quantum sensors to improve measurement precision. Deployment of quantum gravimeters in construction monitoring increased 18% in 2024. 12 university industry consortia focused on quantum sensing research. Government investments in quantum navigation programs exceeded £40 million. United States quantum sensors market forecast 12.8% CAGR from 2025 to 2035, driven by defense applications, satellite navigation, precision metrology. Federal agencies and private enterprises collaborate to commercialize atomic clocks. Magnetometers, accelerometers. Aerospace and autonomous vehicle sectors leverage sensors for ultra-precise positioning. Research in cryogenic and photonic quantum technologies enhances device sensitivity and reliability. Early adoption in industrial automation and geophysical monitoring strengthens market landscape. Over 25 photonics companies involved in quantum sensor projects in 2025. Quantum inertial sensor trials in automotive navigation increased 20%. Public-private funding for research exceeded €50 million in European nations in 2024. No site discovered so far rewrites the entire quantum sensor story. But a journal article published in Physical Review applied. December 2024 examined optomechanical accelerometer search for ultralight dark matter. Device consisted of cryogenic silicon-3 nitrogen-4 membrane cavity, mounted to 4 Kelvin copper plate. Photothermal tuning scanned 39 kHz mechanical resonance. Shot noise limited displacement readout and radiation pressure. Feedback cooling yielded acceleration sensitivity approximately 10 nanoG per root hertz over 30 Hz near resonance. Material inhomogeneity gave access to direct vector coupling to dark matter field. Bayesian search, based on matched filter statistics, yielded upper bounds consistent with thermal noise and above equivalence principal tests. No signal observed, but experiment demonstrated stable quantum limited operation and validated scalable approach to resonant detection. Optimized test masses, lower temperature, multiplexed arrays offer path toward competitive constraints on vector-mediated dark matter interactions. That single experiment shows quantum sensors crossing from metrology into fundamental physics. not measuring known quantities with higher precision, searching for phenomena never detected. Ultralight dark matter remains hypothetical, but quantum sensor arrays provide detection capability inaccessible to classical tech. Every quantum sensor type exploits quantum mechanical properties differently. Nitrogen vacancy diamonds use electron spin and crystal defects operating at room temperature reading magnetic fields at nanoscale. Cold atom interferometers use matter wave superposition of laser-cooled atoms measuring gravity and inertial forces with absolute calibration. Rydberg atoms use highly excited states with giant dipole moments detecting electric fields from DC to terahertz with SI traceability. Superconducting quantum interference devices use flux, quantization, and Josephson junctions measuring magnetic fields at femtotesla sensitivity, requiring cryogenic cooling. Optomechanical sensors use radiation pressure and cavity enhancement measuring acceleration and forces with quantum-limited precision. Single photon detectors use avalanche processes or superconducting nanowires detecting individual photons, enabling quantum communications and ultra-low light imaging. Each platform fills specific application niches: room temperature versus cryogenic, magnetic versus electric versus gravitational versus optical, nanoscale versus macroscopic, portable versus laboratory. Integration determines deployment. Atomic clocks dominate revenue today. Nitrogen vacancy diamonds grow fastest. Cold atom systems lead technical maturity. Future belongs to hybrid integration, multiple sensor types on shared platforms feeding AI algorithms extracting maximum information. The quantum sensor revolution doesn't announce itself. It embeds an infrastructure. GPS satellites carry atomic clocks. Quantum sensors timing signals to billionths of a second, enabling meter-level positioning. MRI machines used NV center-like physics for 50 years before anyone called it quantum sensing. Now, smartphone cameras integrate SPAD arrays for depth sensing and low-light photography. Quantum sensors in your pocket. Oil companies deploy quantum gravimeters, underground mapping density variations, invisible to seismic. Neurologists use quantum magnetometers mapping brain activity through skull without electrodes. Submarines navigate with quantum accelerometers when jamming kills GPS. Climate satellites will carry cold atom interferometers, tracking ice sheet mass loss and sea level rise. Every sensor leverages quantum mechanics to measure what classical physics misses. Superposition splits measurement paths. Entanglement correlates fluctuations. Tunneling amplifies tiny signals. Wave-particle duality turns atoms into rulers. Uncertainty principle sets fundamental limits, then gets beaten by squeezing. Quantum sensors don't just improve measurements, they make impossible measurements possible. Single molecules, single electrons, single photons. Gravity shifts one part in 10 to the 15th. Magnetic fields billion times weaker than Earth. Timing precision, where a 1 second error accumulates over age of universe. These aren't lab curiosities. They're deployed systems, purchased products, industrial tools, medical devices, navigation systems. The transition from quantum physics to quantum technology happens now, in quantum sensing, delivering capabilities classical physics can't match.